Morning. Assalamualaikum. Hi. Yes, welcome back. Can Rick later on meet me at the office? Okay, so we start. We continue. We continue yesterday's lecture, chapter 2, part 2, distribution of the chemicals. Okay, the second step for process synthesis. Before I continue, any question from the previous lecture? Last class we had done on heuristic 5, which do not purge the valuable species, okay, or species or toxic and hazardous, even in small concentration. Okay, next heuristic is focus on the byproducts that are produced in reversible reaction. Okay, reversible in small quantities. Byproduct. Okay, now we are focusing on the byproduct. Okay, these byproducts are usually not covered in separators or purge due to the small quantities. Okay, instead they are usually recycled to extinction. Recycle to extinction, meaning that these byproducts contribute to the reaction. Okay, so that's why it can be recycled until extinction. Means you keep on recycle the byproduct. Okay, until you have the main product. Okay. Small quantities. Small quantities. This one provided that byproduct contribute to the reactions. Okay, if it is not contributing to the reaction, then you can opt to other heuristic, like purging it. Okay. Okay, here when the reaction proceeds reversible, it becomes possible to achieve an equilibrium at steady state by recycling product species, okay, without removing them from the process. Recycle to extinction. Okay, so there are case by case where you can recycle to extinction, where you should purge, where you cannot purge. Okay, depends to your category of the stream, category of your product. But when the reaction proceeds irreversibly, small quantities of the byproduct must be purged. Okay, must be purged. Otherwise, it will build up. Okay, it's irreversible. Even in small quantities, it will build up. So that's why it is recommended for you to purge the byproduct. Okay. Now, when you have competing series or parallel reaction, that your main product, let's say over here, this one example of manufacture of allyl chloride. Okay, this is the main product. Okay. So it has few conditions where if you adjust the rate, the kinetic data, you can produce few of this byproduct. Okay, so that's why it is important for you to know the properties of the component, the composition. Okay, where you can adjust the temperature, pressure, and catalyst to obtain high yields of the desired product. Okay, you should obtain the kinetic data and check before you develop the base case design. Meaning that you see over here, for series parallel and series parallel reaction. Okay, the main product is the B. Okay, so if you have the kinetic data, different condition, you will have this kind of product. Okay, if you go parallel, where here you see parallel, K1 and K2. You get your product and you will get your byproduct as well. Okay, series parallel, you will have few more byproducts. B is your main product. So the kinetic data is important as well. If this is your raw material reacting with Cl2, at this kinetic data, at this condition, okay, at this constant K1, you'll get allyl chloride. But if you provide constant at K2, you'll get this byproduct. Okay, so it's all correlated, the kinetics data, the temperature, pressure, what type of catalyst. Okay. Okay, so before you run the reaction, obtain all the infos. All of this, temperature, pressure, type of catalyst. Certain catalysts will produce different type of products. Okay. Now here, the information that you should require for the reaction. Okay, you see over here the constant. Reaction 1, 2, 3. This is your main product. Okay, so K1, reaction 1. K1, reaction 1. Okay, reaction 1, reaction 2, reaction 3. Okay, so in order to proceed directly to your product, so these are the values that you required. Reaction 1, the K value. Okay, and then what are the temperature, pressure, that one different kind of data. Okay, so here from this figure, it tells you the range of operating temperatures that favors the production of the product. K1, the straight line over here. Okay, K line. So we look at this arrow. So around this figure. So here it brings you the amount of range temperature required. Okay, so the data is important. Now, next heuristic, this one is for reversible reaction. Okay, reversible. Consider conducting them in a separation device capable of removing the products. Okay, so hence driving the reactions to the right. This is the equation for the reversible. Okay, when you don't control properly, it will tend to reverse. Then it will hard to get your main product, to sustain your main product. Okay, example of this, manufacture of methyl acetates with reactive distillation. Reactive distillation. So distillation column, there is one type of distillation that occurs reaction inside. We know generally distillation only separate the feed. Okay, no reaction involved. But there is one type of distillation where we call as reactive distillation. Occurs reaction inside the distillation. So two process in one unit react and separate straight away. Okay, not all reaction can be done in reactive distillation. Now, how reactive distillation works? For example, here we have methanol. Okay, this is methanol and acetic acid. Methanol is more volatile than acetic acid, so that's why it is fat at the bottom. Concentrates in vapor phase, then contacts with acid. Okay, here from the unit op, you see this one is the reaction zone. Okay, it highlights the reaction zone. So methanol fat on the bottom. Which part has higher temperature, bottom or top? Bottom. Right, okay, so bottom. So methanol, that's why methanol fat at the bottom, because it can quickly vaporize. Once it is fat to the bottom, it quickly vaporize. Okay, straight away vaporize, then react with the acetic acid on top over here. When they react, it produces methyl acetate. Okay, methyl acetate, then straight away go to the top to be condensed, Then come out as the distillate. So in this unit op, we push the reaction to the right. Push the reaction to sustain the product so that it won't reverse. Okay, as methyl acetate form, it concentrates in vapor, then leave the tower in nearly pure distillate. Water product concentrates in liquid form, removed from the tower, nearly pure bottom stream. So we want to maintain the water in liquid form. So you must know what are the correct temperature and pressure required. Okay, so that the water in liquid form. What is the boiling point of methanol? Methanol is quite volatile. So you don't need high temperature to vaporize the methanol. From there, you can remain the water in liquid form. So if you give the temperature at the bottom, if you supply temperature at similar to water boiling point, both water and methanol and everything will be vaporized. So it won't work. At the end over here, the distillate, you will mix methyl acetate with the water. Okay, that's why you must have the correct temperature down here. Bottom T. Okay, can Any question? Okay, this is one type of distillation column. If it works with your reaction, you cannot simply use this kind of distillation column. Okay, we are done with the distribution of the chemicals. 7 heuristic overall. Now we move to separations. separation much more simpler compared to the distribution of chemicals. Okay, for separation, we have three heuristics where to separate the liquid mixture using this kind of unit of, okay, it can be distillation, stripping, a few types of distillation. Okay, liquid extraction, crystallization, and adsorption. Not limited to this. It depends what is the suitable unit of for your product. Okay, so let's say your feed enters the reactor, and the product stream is in liquid form. Okay, so your product, perhaps A and B, is in liquid form. So you must separate both of them. This liquid separation system, you can use either one of all of these. Select which one is more suitable to your products. Okay, so from there you can get your products. If the separated component can be recycled, so you can opt to recycle into your reactor. Okay, so for liquid. Now, the next heuristic is attempt to condense or partially condense the vapor mixture with cooling water or refrigerant. If your product is in vapor phase, so suggested to condense your product. Use heuristic 9 just now to split the both liquid products, all liquid products. Okay, let's say here pits A and B enter reactor, you have mixtures of A, B, C, your product. For example, okay, it's hard to separate them in vapor phase. So attempt to condense in liquid form, then only separate all products. The separation over here depends to heuristic 10 just now. Either distillation, any of these, liquid extraction. If your product are mixtures, if let's say your reactor is efficiently working, then you have high purity of your product over here. Okay, then perhaps your final product, you need it in vapor form, so you can remain. Okay, again, it depends to your requirement, product requirement. Okay. Now here, separate vapor mixtures using partial condenser, cryogenic distillation, adsorption, membrane, or sublimation. Okay, almost similar to heuristic 10. Vapor, partial condenser. Okay, if partial condenser, you still have your product in vapor form and liquid form, two-phase, partial condenser. Just now, heuristic 10, full condenser. Okay, then overall, all of the vapor will turn to liquid, then separate them. Now this one, partial condenser. Similar concept, vapor, condense first, then separate the liquid. Okay. Any question on the separation? Clear? Now, this is the summary of the separation heuristic. If the product stream in liquid, when it is vapor and vapor liquid. Okay. Now I move this slide because it all summarized in slide 20 and 21. Okay, for heat transfer. Now heat transfer. We move to heat transfer. Heat transfer, it has two categories, exothermic and endothermic. Okay, what you should do when you have a highly exothermic reaction. Okay, when you have highly exothermic heat of reaction, consider the use of excess of reactant. Okay. One, excess of reactant, inert diluent, or cold shots. And or which one method to implement in your process plant. Okay. Now, excess of reactant we had done previously on the raw material, excess of reactant, where it also applies to when you have feed with toxic and hazardous, so that it completely react with the toxic and hazardous. So apart from that function, it can also absorb the heat of reaction. Okay, excess of reactant. Then inert diluent, again, supply inert to control the heat of reaction. Okay, and also cold shot. Cold shot over here, you cannot simply straight away reduce from high temperature straight away to very low temperature. Okay, you must do it in steps. Okay, you see they are separated into few steps. Cold shot. Okay, separated into few phases until you get your targeted temperature. Why do you need to control the highly exothermic reaction? What? To prevent reaction runaway. Okay, other than that? Other than that? Come again? Safety, yes. Safety hazard. Safety. Safety of the plant, safety of the workers, safety of the equipment as well. Okay, so that one is for exothermic. Now for less exothermic, you can circulate the reactor fluid to an external cooler or use jacketed vessel or cooling coils. Okay, less exothermic. So you can opt to less cost of controlling the heat. Okay, so and also can consider the use of intercoolers between adiabatic reaction stage. Okay, intercoolers. Now for endothermic, similar concept, but endothermic, high temperature or low temperature? Endo. If highly exothermic, release heat, right? High temperature. Highly endothermic, absorb heat. How about the temperature? Low temperature. Yes, low temperature. Okay, so to control temperature for highly endothermic heat of reaction, meaning that the temperature is very low. Consider again the use of reactants. Similar practice. Excess of reactant, inert diluent, and hot shots. Now hot shots to control the temperature. What happens if you don't control the highly endothermic reaction? What is possible to occur if you don't control the temperature? It goes too low, reaction stop. Sure. Possible. Other than that, yes, cryogenic. If you freeze, perhaps you can freeze the unit op. Okay, you can freeze the nearby unit op, perhaps. Okay. These affect the distribution of the chemicals. So your feed maybe can be freeze as well. So then it can stop the reaction once your feed freeze. Okay. Okay, for less endothermic, you can circulate reactor fluid to an external heater. Exo just now cooler, now endo we use heater. Jacketed vessel or heating coils. Also, you can consider the use of interheaters. Just now, intercoolers. When your reaction goes too high, the temperature goes too high, we control using excess reactant, inert diluent, cold shots. Okay. If it goes too low, endothermic, excess reactant, inert diluent, hot shots. Okay, hot stream. Excess reactant and inert diluent, it depends to your reaction. Okay. It is not the same as the highly exothermic. It depends to your reaction. Which inert is suitable? Which excess reactant is suitable? Okay, it's not the same for all process. Case by case. Okay, so down here I summarize for the heat transfer. Categorized into endothermic and exothermic. Okay, when you have exothermic, you go temperature, heat will go high, less or low. So what happens when you have high? Again, excess reactant, inert diluent, cold shots before the process. Okay, if you have less or low, external cooler, cooling coil, jacketed, and cooler between stages. Okay, if you have endo, similar for high. Excess reactant, inert diluent, and hot shots. Less and low, heater. Come again? Case by case. If you need all those three to control the temperature, yes, you can do that. It depends. If required. But usually you will see which one is more feasible, because all of that involve cost. If either two or either one can control the temperature, the reaction, then just proceed with those. You can do all together. Of course, at the end, you can control the heat and the temperature. It's for sure you can control. But then, if one or two steps is sufficient, then you don't need to add on the third method. Okay. Yeah. Okay. Now, last part is the pumping and compression. Okay, this one when you have a vapor phase or gas phase to increase the pressure of a steam. Okay, to increase the pressure of a stream, increase pressure of a stream. Pump a liquid rather than compress a gas. Okay, that is condense a vapor as long as refrigeration and is not needed before the pumping. Okay. Why? Because of the cost. Increase the pressure of the stream. Okay, if you want to increase the pressure of the stream, pump a liquid rather than compress a gas. Okay, always preferable to condense a vapor, pump it, and then vaporize it again, rather than compress it. Here, let's say you have vapor, so condense it to liquid, then pump it. It is easier to work this way, and the cost is lesser compared you compress vapor to vapor. Okay, this one, the function is to increase the pressure. Increase the pressure. The condenser and heater over here, you can use heat exchanger. Okay, perhaps you can design your heat exchanger network to increase and lower the temperature. Okay, the main concern over here is pump a liquid. This part, pump the liquid rather than compress the vapor. As it mentioned over here, for cheaper to pump a liquid rather than compress a vapor. The cost of compressor is higher compared to cost of pump. Okay, this one illustration of the pumping liquid. Okay, here is the pumping liquid. You focus on the pumping liquid first. From liquid, you can pump, push the liquid then to the next level. Okay, increase the pressure. Whereby for the compressor, you can see how it works. And compressor also has few types. This is piston type, and then this is centrifugal type. Okay, it depends which type that you require. This one is additional slide. Okay, so here air in, then air out. Sorry, not air. It depends to your vapor or gas. Okay, so it requires specific type of compressor. It depends. Remember, compressor works with air, vapor phase. Pump work with liquid phase. Okay, there is always in PDP, students sometimes use pump to increase the pressure of vapor stream. Okay, so you must use the correct instrument to increase the pressure of your stream. Check the phase of your stream. Liquid, use pump. Gas, use compressor. Okay, that's the fundamental. Cannot. Okay, this is the summary of the heuristic. We have 5 category. Okay, the raw chemicals. Yeah, the raw chemicals which involve the reactions, distribution of the chemicals, the input and output, the recycle system, the separation. Okay, sorry, separation over here. Separation. Then the heat transfer, exo or endo. You need cold shots or hot shots. Okay. Then the last part is the pumping and pump and compressor. These two, 1 and 2, basically involve at your reactor. Okay, where feed for your reactor. Wait, I draw it. Yeah. Okay, what I can conclude is number 1 and number 2, the raw materials and chemicals reaction. So basically it involved with your reactor. The feed and the product. Okay, so the feed over here, it depends to this, your raw materials. Okay, inside the reactor occurs the reaction. Okay, here it occurs the reaction. Now it refers to this. How is the reaction? It also involves this. Okay, so both 1 and 2 refers to your first part of a process when it involves the reactor reaction. Okay, after you get your product, then you need to think of how to distribute, to separate it. Okay, then after you finalize all those things, then only the step 5 comes in, task integration. you connect all each of the unit op into one complete link. Okay, any questions so far? Those are the important heuristics that you should focus on. There are many more heuristics. Okay, there are many more heuristics, but those are the most important one, the one that we discussed. Okay. Can. Now we move to steps in designing chemical process. Do you want 5 minutes break? Okay. Okay, we take 5. Those who haven't captured the attendance, snap.
Yeah, that's a different shape. But what is a joke can be? I like Yes, it's gonna be like 3 months to get back. By if I just reinforce it from the okay, I know you do it. Yes. That's would you like some exactly? It's bigger rich talk up. You got one poison and you like this one. And you think bad. Yeah, that's That's the fact. My first thought as I I saw like so I feel like your life has not been trained that I should put something It's like socks and honestly, Try not to say. 甚至中国的在用。About very about that is just long.
Okay, 5 minutes. Now, after we are done with the heuristics, everything, are you ready? 5 minutes are up. Okay, can we continue? Now, we are done with the heuristics. We move forward into steps in designing the chemical process. Okay, I will use an example of the VCM. This one you can read through all the recall slide. Okay, I will skip to here. This one, as discussed earlier, these are the process synthesis. Okay, process synthesis, the 5 steps. Last one, after we the heuristic, the heat exchanger, everything, and the pump compressor, then only integrate everything into one PFD. Okay. This one is a repetition from the previous part. Okay, I'll skip to this. Process creation and development of base case design. So we will use example of VCM. Again, the VCM, the one that we discussed, the alternative synthesis last time. Okay. Now we go one by one, the step. Okay, these are the possible reactions to produce VCM. Possible reaction to produce VCM. Okay, here it mentions 5. In your PDP, I think at least you should have 3 pathways. Okay, 3 reactions to compare. Okay, so these are the possible reactions to produce VCM. C2H3Cl. So the circled one is your product. Now the first step is to eliminate the differences in the molecular type. Eliminate differences. So from the 5 alternative pathways, you should compare the properties. You should compare Here you see this is your main product, the VCM. In some of the reaction, you have byproduct. Okay, byproduct, which is HCl and water. Okay, your feed, you either need C2H4 or C2H2. Okay, so you should compare all of these properties. List down in the table. Okay, finalize its properties. What are the molecular weight or listing? Okay, why? Because that one will be used in your reaction. Okay, we go one by one. Step 1, to eliminate differences. First, we compare the advantages and disadvantages for each pathways. Okay, select this one is direction 1. See what are the advantages. Okay, so here advantages, it can occur spontaneously at few hundred degrees C, meaning that the reaction rate is fast to get your product. Okay, the disadvantages does not give high yield of VC without simultaneously producing large amounts of byproduct. Okay, expensive chlorine may produce byproduct which may not be sold easily. So each of the pathways, you must list down what are the advantages and disadvantages. In your PDP, I think it is better for you to put in a table. Then you rate it. From there, you can see the ranking, which one to choose. Okay, next pathway, which is hydrochlorination of acetylene. So you list down again the advantages and disadvantages. Do the same for each pathways. Okay. Okay, that one is for step 1. Now here it concludes from the comparison just now. Reaction path 1 is eliminated due to its low selectivity. So you decide which pathways to be eliminated and you should know why to be eliminated. Okay, so this lists 4 alternative paths. Now you left with the 4 alternative paths. That one you think that is can meet your product requirement. Okay, then you should compare the gross profit. This one only gross profit, not economic analysis yet. Okay, gross profit. Gross profit over here, you compare your product minus your reactant, minus your feed, whatever you need. The simplest part to do the analysis, gross profit. Okay, that's why just now the information, chemical formula here, everything is important so that you can know what are the costs per kg or per ton. It depends on what basis that you want to compare. Okay. Now here it consider reaction path number 3, where the number 3, this is the product and reactant. Compare the cost. Okay, so product minus the reactant. This is for product minus your reactant. You get positive, so still profit. Roughly, still have profit. Okay, this one path 3. This one have profit. Okay. Now again, estimate for the rest. Assumption complete conversion. Okay, without any side reaction. So just to roughly calculate the gross profit. Now, when you do for the rest of the pathways, remember the first pathway we have eliminated. So left with 2, 3, 5. Do the same for the rest, then you should compare what are the gross profit for each. Okay, from this table, you see reaction 2 is a loss. Okay, so don't bother to proceed with this reaction. It's a loss. Now, focus on reaction 3, 4, 5. All have profits. Okay, this one without considering the capital cost anything yet. Huh? So acetylene here it concludes reaction part 2 is negative, which acetylene is very expensive to ethylene. Acetylene. Okay, the C2H2 acetylene. Now we can remove reaction 2. Here it choose reaction 3 because from the gross profit comparison, it gives higher gross profit. Okay, so we will focus on reaction 3 because it gives higher gross profit. Now we proceed with reaction 3, then we check for the rest. So for reaction 3, this is the feed, this is the product. Okay. Identify the feed and the product. So eliminate difference still at the first stage. First step, huh? Identify what are the feed and the products. What are the targeted production. Okay. Now from there, distribute the chemicals. Okay, wait before we go to distribute. For eliminate differences, still remember what is the heuristic. Eliminate differences. Okay, we check back what are the heuristics. Here, raw materials and chemical reaction. Only one heuristic, which you should select the raw materials and chemical reaction to avoid and reduce all of this. Okay, so this one, we had done the comparison. Which one is better? For step 1, only one heuristic. Wait, I open the summary. Is it? Okay, this one. Heuristic. Step 1, only one heuristic. Then we move to step 2, distribution of the chemicals. So let's see whether it meets any of these heuristics. We can apply any of these heuristics. Okay. Okay, now we go for distribute the chemicals. Few points need to be taken into consideration. We identify chlorine and ethane as the feed. Okay, what are the production rate that you need to identify? What are the conversion? So at the moment, at the first stage, you assume 100% conversion. Okay, but after you simulate, only 60% of the C2H4, the VCM, is converted. Sorry, C2H4Cl2 here. Yeah, feed Cl2 react with ethane, enters the direct chlorination process, then you produce this. Okay, this is not yet your main product. Then it goes to pyrolysis to produce the VCM. Okay, so from there, you can try to calculate through material balance how much is your product. What is the conversion rate of your product from there? Okay. Okay, from the the material balance, then you should calculate what is your targeted production based on your targeted production. How many tons per day or per year? Okay, you should calculate based on your material balance. Okay, step 2, you need to identify what are the reaction involved in between these two stages and what happened, what are the material balance, how many percent of conversion, okay, what are the yields. Okay, the one for step 2. Now we move to step 3, eliminate differences in composition. So after your chlorination reaction, nearly pure and requires no purification. Okay, here after chlorination, nearly pure, you get C2H4Cl2, dichlorine. Now this one is the one that feed into the pyrolysis to produce your VCM. Okay, VCM. So after the chlorination process, requires no purification. But after the pyrolysis, which only 60% conversion, where you have the byproduct. Okay, after the pyrolysis, you have HCl, VCM, and the C2H4Cl2, the dichlorine. Here you need to separate. You need separation unit off. Okay, in order for you to separate the C2H4Cl2 back to your feed of pyrolysis. Okay, this is your feed to pyrolysis. These byproducts contribute to the reaction, so you can recycle back to the feed. Okay, then here you must put 1 unit op to separate the HCl and the VCM. Okay, how to separate this VCM and HCl? It depends to the properties. You need to identify what is the separation unit that is suitable to separate the HCl and VCM. Check out what are the phases involved. Okay, what are the unit op required? How many unit ops required for the separation in order for you to achieve pure VCM? Okay. Now from here, you can see HCl for boiling point. Boiling point is this. So what phase are there in after the pyrolysis? This is the boiling point at STP. Okay, HCl, this one. After the pyrolysis, what phase do you think HCl and VCM in? Yes, vapor phase. So both in vapor phase. So you need to identify what is or are the suitable unit ops to separate these two. These properties will help you to identify. Okay. Okay, then it's suggested distillation column. Two distillation column to separate the VCM and the HCl. Okay, remember that product from pyrolysis is in vapor form. So do you need to liquefy the vapor to enter the distillation column or not? You need to think. The feed to distillation, it should be in liquid or can be in vapor. Huh? Liquid. Should be in liquid. Then you should propose or suggest or look through what are the required instrument or unit op to install before the distillation column. Okay. Then from there, identify what type of distillation column that can separate the HCl. Okay. Then the choice of distillation tower for the next one. What are the what are the options that you have? Okay. Step 3 just now, eliminate differences, meaning that the separation part. Okay, it involves the separation. Okay, step 4, which is to eliminate differences in temperature, pressure, and phase. Now you see the PFD now become more complex, where you need to consider the temperature, pressure, and phase change. What are the unit of the instrument that you need to fulfill the requirement? Okay, so product stream over here. Here it mentioned 90 degrees. To enter the pyrolysis, you need up to 50 degrees C. So what you need along the way before the pyrolysis? Okay. Now here you see, after the pyrolysis, just now you mentioned in vapor form, right? So here now it identify to change the temperature and phase. Okay, that is step 4. Eliminate differences in temperature, pressure, and phase. Any stream that requires temperature change, pressure change, phase change, you need to identify. Okay, so after you identify all the unit ops, the tasks, connect them all together in one process flow diagram. Okay, so from here, you can see the overall PFD This is your input. Okay, this is the feed. Okay, this is the feed product. This is your separation. Step 3 just now. Okay, so this one, the step 4, the one that involve evaporator, phase change, preheater. This is your pyrolysis, the main unit of, one of the main unit of. Okay. Now, before entering the pyrolysis just now, you need to heat up the stream. So this is what you need. After pyrolysis, the product stream, you need to change the phase. So this is what you need before it enters the distillation. Okay, after recycle, the bottom product after the second distillation, the byproduct that you want to recycle into the pyrolysis. Okay, this part. So here you need cooling water. Okay, so this we can call as the overall PFD now. After you consider the 4 steps earlier. Identify the input-output, identify the distribution of the composition. Okay, how do you want to distribute it? Then the separation, then the temperature, pressure, phase change, then finalize in one PFD. Okay. Clear? Any question? This is the assembly of synthesis tree. Just summarize the synthesis that you have done just now, where we choose reaction tree because of the high gross profit. Then proceed from there. Okay. This is the more complex. This is the instrument and the equipment. Okay, you can read through the summary table. Okay, your PDP, you should consist of this summary table, stream summary table. Okay, stream summary table. This is important. Huh? So in PDP, please include the stream summary table. Each stream, what is in each stream and what are the conditions, temperature, pressure, all those things. Okay, what are the composition of your stream? Usually the examiner will see in each stream whether it's tally or not. Last time I evaluated the UTM one. I share my experience. There are contradicting from the stream summary table with the PFD. You will see some types of examiner very strict. They even calculate the amount, whether it's true or not. Okay, so please do not simply put any amount. You must make sure it all correct. The info is correct. And you should be able to justify, to explain what happened if phase change, the temperature, pressure drop. Should be able to explain that. Okay. Perhaps next class I can share with you their stream table summary. Okay, so to make sure you understand this chapter 2, I want you to do one exercise, which is a group activity to implement the synthesis step. Okay, it is better to form a group, work in group. Propose one product manufacturing process other than the VCM. You can use perhaps your PDP. Implement these 5 synthesis steps until you can generate the PFD. Just a simple one. Simple. Don't need to identify 5 major equipments or anything. Just a simple process. I want to see you implement these steps. Okay, assign one leader. Then only the leader submit the exercise by Monday morning before our class. Monday is what date? 29. I will share with you the link for submission. Okay. The purpose is I want to see you all can understand how to implement these steps. Okay, not only listen to my lecture. You should be able to understand because in the midterm and final exam, you must know how to do this. Okay, any questions? Do in group, do not do individual. Okay, so that's all for today. See you next Monday. Submit before the class so that we can discuss during the class.